Hello, this is John Chen, and today's topic is about generative models. We'll go through the contents starting from how generative models emerged in replace of the discriminative models and focus on the linear and quadratic discriminant models. Further, we'll also see the naive Bayes with Gaussian distribution, matrix form of them, and Bias-Variance Trade-off property. After solving the problem, I'll briefly introduce the modern trends related to LDA and QDA. In previous chapters, we have learned the discriminative models like logistic regression. However, these methods have several problems. Regarding to the first case, when the data are substantially separable, there could be some problem. Logistic regression could be expressed like the equation, and we have to find the maximum likelihood which has a value between 0 and 1. When the data are extremely separable, the likelihood can reach 1. That means the log likelihood for each class goes 0. Therefore, the coefficients goes to infinity, and we cannot estimate the formula. Logistic regression performs well with large sample sizes, but when the sample size is small, it tends to overfit the few available data points and fail to generalize. In this case, generative models like LDA and QDA can perform better. And for the third problem, the logistic model is suitable for two-class classification because the logistic regression implicitly assumes an order among classes when extending to more than two categories. This works for ordinal cases like ice water vapor, which has hierarchy, but not for categorical cases like cat, dog, and bird. Even though there is no hierarchy, logistic regression imposes an implicit sequence among them. To overcome these problems, generative models estimate the class conditional distribution directly, avoiding the hierarchical constraint. Generative model starts from Bayes' theorem and model how the data are generated for each class. If we put the conditional probability equation to the original form of Bayes' theorem, we can compute the posterior probability used for classification. Both discriminative and generative models estimate the posterior probability, but they take different paths. A discriminative model like logistic regression directly models the posterior probability using a function without describing how the data are distributed. In contrast, a generative model such as LDA and QDA first models P of X given Y and the class prior pi, then combines them using the equation to obtain the posterior probability. If we assume that the class conditional distribution follows a Gaussian distribution in generative model, this becomes LDA or QDA. The formula leads to LDA when the variances are equal for each class. Therefore, the equation of LDA can be expressed as this formula shown below. In the LDA, the curve shares the same shape, only shifting along the mean values. This means the model separates classes mainly based on how far their means are apart, not by changing the shape of the distribution. The overall height of each curve differs according to the prior pi k, which reflects how common each class is in the data. For example, during the rainy season, the prior forecast rainy is higher than sunny, so the model is more likely to classify data as rainy under the same conditions. By multiplying the likelihood with the prior pi k, we get a weighted probability which has different height depending on the class. The cross-section of the probability denotes the boundary of the two classes. We can take the logarithm to simplify the product into a sum. And by removing class-independent constants, we obtain a discriminant function that depends on x. The class with the higher delta k has a higher posterior probability. When two discriminant scores are equal, that point defines the decision boundary between the classes. This gives the first order equation in X. Solving it yields the exact boundary location, which depends on the class means, shared variance, and priors. Since the boundary is linear in X, LDA produces linear decision boundaries, and in a one-dimensional space, this appears as a single point dividing the two classes. When we relax the constraint of LDA, the model becomes quadratic discriminant analysis. Because each class can now have its own variance or covariance, the distributions can intersect more than once, resulting in nonlinear quadratic decision boundaries. In QDA, each class has its own covariance, so we can no longer remove the class-independent terms in LDA. As a result, the discriminant functions keeps the quadratic term, making the decision boundary nonlinear. Similarly, we can get the boundary by setting delta 1 is equal to delta 2. The resulting equation contains an x squared term, forming a second-order equation. This shows that QDA produces quadratic decision boundaries. However, in one-dimensional case, the boundary only appears as 1 or 2 points, so the quadratic nature isn't visually apparent. Naive Bayes is another generative model that assumes features are conditionally independent given the class. This means the joint probability can be expressed as a product of individual feature probabilities. Although it can use any distribution, we often assume each feature follows a Gaussian distribution with its own mean and variance. When we have more than one predictor, we represent the data in matrix form. Here, x and mu k becomes vectors, and variance generalizes to the covariance matrix, which captures the relationships between predictors. From the definition of the variance, the covariance matrix takes this formula. And when calculating this, the off-diagonal terms have the same values, thereby the covariance matrix becomes symmetric. In matrix form, the likelihood is given by this formula, and if we remove sharing covariant metric constraints, we get QDA, which use only n divided by k samples for each of the covariance. Finally, in the naive Bayes case, we assume the predictors are independent, so all off-diagonal terms in the covariance matrix become zero. When we combine the assumptions from LDA and naive Bayes, the distribution can be visualized in a 2D space like this. Since all the classes share the same covariance, so the ellipses have identical shapes, naive Bayes adds conditional independence, which makes the ellipses align with the coordinate axis. If we remove the independence assumption, the model becomes LDA. Now the covariance matrix includes off-diagonal terms, meaning there is correlation between x1 and x2. As a result, the ellipses no longer align with the axis. They rotate according to the covariance. If we relax the shared covariance assumption, the model becomes Gaussian naive Bayes. Instead, if we remove the diagonal assumption, we obtain QDA, where each class has its own covariance matrix. Because the class variance differs, the ellipses have different shapes, and that's exactly why QDA produces a quadratic decision boundary like the gray line here. The difference between LDA and QDA boundaries reminds us of the bias-variance trade-off. LDA models like linear models like LDA or linear regression have higher bias but lower variance. In contrast, more flexible models such as QDA or nonlinear regression have lower bias but higher variance. Similarly, QDA's decision boundary is more flexible than that of LDA. Because of this increased flexibility, QDA tends to have lower bias but higher variance compared to LDA. So while LDA provides a more stable and generalized boundary, QDA adapts more closely to the data at the cost of higher variability. We now examine the differences between LDA and QDA under different conditions. Each sub-question A to D compares their performance on training and test sets or under varying sample sizes. The problem is asking about the bias-variance trade-off results in different given conditions, because the main difference between LDA and QDA usually derives from their bias-variance trade-off. In part A, the problem is asking if the true boundary is linear, which model, LDA or QDA, would perform better. In the training set, the model directly minimizes error, so the more flexible QDA can fit data points more closely, just like nonlinear regression fits every sample better than a straight line. Here's the same idea visualized. When the true boundary is linear, both LDA and QDA can approximate it, but QDA's curved boundary can shift slightly toward each data cluster to reduce error. In this example, LDA misclassifies 5 points while QDA only 3. So QDA achieves a lower training error. However, since the true boundary itself is linear, LDA can also perform quite well. Therefore, the performance of LDA is generally less than or equal to QDA on the training set, meaning QDA might slightly outperform due to flexibility, but not always significantly. And for the test set, although QDA performed better on the training set, it was fitted only to the seen data. For unseen test data, QDA's flexible boundary may deviate more from the true boundary, as shown by this red distance. This is overfitting. Because QDA is more flexible, it can fit training data too closely and perform poorly on the unseen data, especially when the true boundary is linear. This happens due to QDA's higher variance. So when the true boundary is linear, the test performance of LDA is generally better or equal to QDA. Now in B, the true boundary becomes nonlinear, shown in purple. And just like the training set, QDA can flexibly adjust its boundary toward the data point. This reduces bias and gives lower training error compared to LDA. So when the true boundary is nonlinear, QDA performs better on the training set. However, in the test set, for a nonlinear true boundary, the bias between LDA and the true boundary is much larger than the potential overfitting risk of QDA. So QDA actually performs better here as well. The gap between the true boundary and LDA's linear one is significant, meaning LDA can't perform generalized well when the true boundary is curved. Now let's move on to part C, which asks about how the sample size affects the test accuracy of QDA relative to LDA. We already learned that the discriminative model also performs better with larger sample size. Then how about the generative model? This part connects back to what we discussed in A and B. When the sample size is small, QDA's high flexibility can cause it to overfit the training data, even when the true boundary is nearly linear. So in small sample situation, high variance and low bias of QDA lead to unstable performance. One reason for this instability is the influence of outliers. When the sample size is small, each outlier has a much larger effect. Because QDA is more flexible, it even tries to fit these noisy points, which increases its variance. You can see the shape of boundary differs largely when the training set differs. LDA, on the other hand, is less flexible, so it's less sensitive to such outliers. As the sample size increases, however, the effective outliers decreases. The variance of QDA becomes smaller and more stable. Consequently, QDA's performance improves and gradually becomes comparable to or equal or even better than LDA, especially when the boundary is nonlinear. We can also explain this mathematically. QDA estimates separate covariance matrix for each class using fewer samples, while LDA ensures a single covariance across all classes effectively using all n samples. So when n is small, QDA's covariance estimates become unreliable, increasing its variance. As n grows, this difference becomes negligible and QDA's estimates stabilize. Finally, Part D asks whether QDA can achieve a better test error rate even when the true boundary is linear. Recall from Part A, LDA showed higher test accuracy when the true boundary was linear. Now, even though QDA is flexible enough to model a linear boundary, we should not ignore its higher variance. If the true boundary is linear, LDA already achieves almost zero bias with low variance, while QDA's flexibility adds a necessary variance, increasing test error. Therefore, the statement is false. QDA does not outperform LDA in this case. To conclude, QDA performs better when the true decision boundary is nonlinear or when we have enough data because its flexibility can reduce bias. However, when the true boundary is linear or the sample size is small, LDA tends to perform better due to its lower variance and higher stability. So this entire comparison between LDA and QDA clearly reflects the bias-variance trade-off. LDA is higher bias but lower variance, but QDA has lower bias but higher variance. Therefore, the optimal choice depends on the boundary shape and the amount of data available. Next is about additional materials. As we saw in the matrix form of LDA and QDA, both methods estimate the covariance matrix for each class. However, when the number of predictors P is greater than the number of samples N, this covariance matrix becomes singular. That means it cannot be inverted. This problem is particularly severe for QDA since it estimates a separate covariance matrix for each class using only n over k samples. In modern data, it is common that the number of features P is larger than the number of samples N. Under such conditions, both LDA and QDA can fail since their covariance matrices become unstable or even singular. To address this issue, a modern method called regularized discriminant analysis, or RDA, was introduced. RDA combines the covariance metrics of QDA and LDA through a regularization parameter lambda, as shown here. When lambda equals 0, it becomes QDA, and when lambda equals 1, it becomes LDA. By shrinking the unstable covariance matrices and QDA toward the pooled estimate from LDA, RDA reduces the variance and prevents overfitting while keeping flexibility. Therefore, RDA is more flexible than LDA, but more stable than QDA, making it a balanced and robust approach for high-dimensional or small sample problems. Similarly, other modern approaches like convex LDA reformulate the LDA object to avoid matrix inversion, especially when the number of predictors exceeds the number of samples. Unlike the original LDA, which minimizes the ratio of scatter matrices, convex LDA minimizes a convex summation term, ensuing a global optimum without inverting any matrix. This is particularly useful for genomics. RNA sequence data contain tens of thousands of predictors but very few samples. Such data are sparse, noisy, and unstable for inverse matrix-based optimization. Convex LDA provides a stable and efficient alternative that performs well even under the extreme condition. To summarize, linear discriminative model assumes equal covariance and produces a linear boundary, leading to high bias but low variance. But QDA, on the other hand, allows different covariance for each class, giving low bias but high variance. Depending on the data set, whether it's small, noisy, or nonlinear, we need to choose an appropriate model that balances this bias-variance trade-off. This concept also forms the bias for a basis for more advanced methods like RDA and convex LDA, which bridge these two extremes.